then we have a morphism of locally linked spaces from S to Y. Then we get the functor from scheme which is locally of finite type over K to the category of adic spaces over super KV by attaching X to X add, which should be the fiber product of X and super KV. Then this is a comparison map, a very, very natural construction. This is actually what we want. So let me give one example. It is not free-faced, I think. I think so.
But if X is proper over K, you have the same Gaga, that would be the case when X is over K.
Sorry?
When X is proper over K.
Yes.
Or when you work with schemes proper over K, presumably you have the same GA field.
Yeah, for coherent cubes, you say? Yes, it is known.
Okay. So if you work with schemes that are proper over K, then this is restricted and is fully based.
Yes, I think so. So the example is that X is equal to A1K. So it is a very fundamental example. This is a spectrum, spec K bracket T. Then X add is the union of this analytic spectrum. And this analytic spectrum is a disk with radius pi, absolute value of pi to minus n. So if we take a union for all n, then the radius becomes greater, bigger and bigger. And if we take a union, then we get the rigid space, which is actually an affine line. So, of course, this is not quasi-compact. A1 is not quasi-compact in the theory of rigid spaces, or of course in the theory of complex geometry. So yes, it is very strange that in the algebraic geometry A1 is quasi-compact. So the topology is a very weak one. So it is easy to verify the universality property. It satisfies that universality property. And I will explain the relation between this construction of comparison map, comparison functor, and the generic fiber I explained before. If X is a proper, it is very important if we want to study the bad reduction of similar varieties. The proposition is that if X is proper over K, and take a compactification of X over V. We assume that this is also proper, so this is a compactification over V over V. So we always take such a compactification. Then the genetic fiber of the completion of this proper scheme is isomorphic to X add. So if X is proper, we can construct a comparison factor by using the genetic fiber. So these two constructions are compatible.
You don't need X bar left over.
No.
Just any.
Yeah. Okay.
Compactification just means such a proper.
Oh, and this is Cartesian. I need it. But if X is proper, then just taking a scheme theoretic closure in it, we make this diagonal Cartesian. So
you mean any compactification of it?
yeah,
Any compactification.
anything is okay. Okay. So I have 20 minutes. Yeah. So in the remaining part of today's lecture, I will explain about the definition of etale map and smooth map in the category of adic space to define an etale cohomology. So, but it is almost the same. So for etale or smooth morphism of adic spaces. But to make the definition simpler, I will assume that all adic space in this section is analytic. Let X be an adic space, and a point of X of X is said to be analytic point if and only if there is a affiliate open neighborhood of X such that the global section of the structure sheaf is tailoring. Namely, it has a topologically nilpotent unit. This is the definition of analytic point, and if so X is said to be analytic if and only if every point of X is analytic. This definition is so simple, but it is difficult to understand. So this remark is useful for understanding the meaning of analytic point. So assume that X is affinoid spot A. Then a point X corresponds to a variation on a triangle, and the variation continuous variation V is analytic if and only if the support of V is not open in a triangle. So the example is this one. So super VV consists of 2 points. And if is first we take modular pi map and take a trivial variation. So support of S is equal to the pi V, and it is open. So S is not analytic. On the other hand, the support of eta is, so the definition of eta is that we embed this V into K and take a variation of K. So the support of this eta is 0. And this is not open. Therefore, eta is analytic. So this point has a flavor of rigid analytic geometry because it comes from the variation on the fraction field K, the complete variation ring. On the other hand, this S is something strange one, and it is not analytic. It is it has more algebraic flavor. And technically, it is convenient to assume that every adic space is analytic. So I will assume that.
We know something like generic fiber performance scheme is analytic.
Yes, it is analytic because a point lying over a analytic point is again analytic. Whether it's not true, but anyway, that is true. So non-analytic adic space is also useful for considering some nearby cycle or something, but for the rigid geometry, it is not necessary. So let me define some definition. So for the affiliate ring, we can naturally construct the formal convergent power series of it. So this is again a pair of this and something here. And this is actually a convergent power series on this f-adic state ring, this f-adic ring. But to define it, we have something to do. So consider the convergent power series on this and take integral closure and something. So I skip the definition of it. We can define it. So so the definition is that the map from Y to X, the morphism of analytic adic space is let F be a morphism analytic adic space. And F is said to be locally of finite type if for every, so it is very usual definition. So for every y in this y, there exists a affinoid open neighborhood. Affinoid open neighborhood containing y, and there is also a affinoid open of fy containing fy. This is a similar one. Such that so the image of V by F is contained in U, and and OXU, OX plus U, from here to the section on V is finite type. Finite type. What is finite type? If we put A, this, if we write A for this and B for this, then finite type means that B is isomorphic to A T1 to Tn quotient by some ideals. As topological ring. So we consider this ring, we consider the quotient topology on this ring, then this is isomorphic. This is the definition of locally finite type. And of course the finite type means that space is compact and locally finite type. So we can define so finite type, locally of finite presentation and finite presentation in an obvious manner. And let F be so if F is said to be etale, if this is again a usual definition. So F is locally of but it is not important. So 短いやつ聞かないな。Okay. So there exists. So for every y in y, there exists u and exists. So sorry, this is v and exists u as above, and such that B triangle is isomorphic to a triangle bracket T1 Tn quotient by F1 Fn as topological a triangle algebra such that the determinant of Jacobian is invertible. in this ring. So invertibly in this ring, in right hand side. This is the definition of etaleness. It is similar as the definition of schemes, etaleness of schemes. Sorry? Oh, yes. Thank you. Actually, we can define etaleness by using some lifting properties or flatness and unamplifiedness, or by using some differential forms. So the situation is similar to the case of schemes. And finally, I will define the smoothness. Let F be a smooth. So we call F smooth if for every, so if roughly speaking, it means that locally F is a fine vibration. So for every y in y, there exists V U. So open neighborhood of y, and there exists U. This is affinoid. Open neighborhood of Fy, and we put it super A such that Fv is contained in U, and for some n, there is a etale map from V to the super A bracket T1 to Tn, and Uf, this is equal to super A. This commutes. Normally, this map is etale locally affine, so not affine, but disk vibration, constant disk vibration. This is the definition of smoothness. So finally, I give a definition of rigid space, and tomorrow I will use this definition to define the etale cohomology. The definition of rigid space is, now it's very simple. Let K be a non-Archimedean field. A rigid space over K is an adic space which is locally of finite type over super K circ. This is a variation ring of K. And it is known that the rigid space over K is locally isomorphic to super AA circ, where A is the quotient of the convergent power series ring by some ideal. We know that this is Noetherian, so that this ideal is always finitely generated. So this is if you know the classical theory of rigid analytic geometry by Tate, this is compatible with the definition of Tate. And actually the attachment from the Tate space to the adic space, that functor is free faithful. So the theory of adic space contains the theory of classical rigid spaces. I will stop here. Thank you very much.